So relax, we are nearly on time. That's right. Gonna have some water right now, right? Okay, so this is a very large subject I'm trying to address, and therefore I will be quick on some of the slides, just flip through. Some of the key message was already published, in fact, just published. As I said, because we have been working on this for the last 4 or 5 years, so we have more than a dozen papers. The reason I can be fast on some of those slides is because many of these papers are already available to you. And I will be very sketchy also in the sense all the details is in my book that I'm struggle to finish it this year. And the bulk part of this book is on fracture mechanics. And I just recently added the topic of adhesion as the last chapter. So we all go back to the beginning, 70 years ago. And this phenomenon just intrigued me as one of the most intriguing polymer physics problems. You take a piece of rubber, cross-link, you stretch slowly, it breaks here. If you stretch faster, it breaks much later. If you stretch faster yet, it's more stretchable. And if you go to lower temperature, it can stretch more. So what was plotted y-axis is how much it can stretch versus the rate you use to stretch. And different curves are just different temperature. The higher temperature, as I said, allow you to stretch more. And this feature is also observed, and so we say, as I said, it's stronger when you're faster, it's stronger when you're at lower temperature. And this feature also is true for so-called fracture type of problem, that you can mimic that by tear. And you find, again, the resistance to tear is higher when you tear faster, higher when you go to lower temperature. Well, since the guy who worked with this problem is Ferry's student, he says, if you have this, I do a horizontal shift, I have WF. You can do the same with the toughness problem. So the question is, how on earth the temperature decrease give you stronger material? Conversely, how come you can be tougher when you try to tear faster? It all traces back to my dear colleague. So Beakey is a very famous polymer physicist of his time. He later came to Akron to be the faculty. Everything, you can blame everything. I will not go to the details of why he came up to this point, but basically he explained, he thought he understood why faster stretching will give you a stronger material. Let me explain, put everything in his mouth. Here's what happens. You one rate, you stretch to some level, that's the level chain stretching. He thinks if you do it faster, which is red, the system spend time to get to the level of stretching, which means you can stretch there and sit, you have to wait, the chain will have to take time to become elongated and eventually suffer transition. Similarly, since it doesn't stretch to that level, I can stretch more so that eventually I reach higher stretching. And this in severe violation of what we believe in, which is affine deformation. That works very well. So let me conclude. He and his co-workers essentially made this conclusion, that your dear polymer spend most of the time trying to reach to the level of chain stretching, and the time it spent to break the chain is negligible. I want to show that's exactly the opposite that's true, based on experiment. Moreover, there's this more magic experiment. You do a step stretching. You find if you stretch to this level and you do it at the lower temperature, it will this is called delayed rupture. You hold it over time, it will rupture. The more you stretch, then you wait less time for rupture to occur. Lower temperature, it takes longer time. That's all in there. Notice that parallel curve. You can do a WF shift again. And in fact, he did. And he compared with WF. That's the red is WF, the other symbol is data, except if you shift, you realize it systematically deviates from WF. I'm going to run out of time like no tomorrow. So I'm going to cut the chase. There's so much to say. Basically, the essence is to learn about whether this rupture problem is dictated by flaws or not. The short answer is no. How do I know it? Is because I need to know the strength of the material. I find using this technique that the strength of the material is the same as you could observe from a notched sample, where I know this movie to us is already boring. We have seen it for years, actually. So you can access the stress at the tip. You find that stress level is the same stress level that you find when rupture occurs in an unnotched sample. I know there's a lot to speak about, but nevertheless, I have to skip all this. In any case, let's get to the bottom line. Evidence one against Beakey, Halpin, and Smith. So this is performed by either step strand fast to the same strand or continuously stretch to the same strand. Both cases leads to breaking. This is the actual data. So I wish I should have let that movie loop to play. So basically, in the step strand, what they're waiting for, there's no change. There's no change in birefringence. Your dear polymer instantly, because it's a strand-controlled experiment, its chain reaches the strand right away. They are waiting for what, right? Similarly, in a continuous stretching experiment, you stretch faster than, let me show you the next experiment. You stretch faster than, by the time of stretching to a certain level, the low stretching rate has already spent lots of time. But notice, their birefringence are all the same. So what this poor guy has to do is, the lifetime is so short so they can stretch further. So by now, I hope I hope this kind of experiment showed you guys that this thing is really suffering the molecular strand right away. They are waiting silently for something to happen. So we recognize that this something it has to do with breaking chains. So it turns out you can do a DFT calculation. You find the lifetime of the carbon-carbon bond, and you can make a jump and think about how a chain break. You can make a further jump to think about how a network break, and it's all about the fact that your lifetime gets shorter of your network as you stretch more and more. So you can play with this game, but basically I had this biggest assumption that the reason rupture occurs is because your network expired because you have given enough time, and that network lifetime is shortens in the red line. So in any case, I skip all this, and this is almost one of my last slides. How much time do I have, actually? What? 2 or 3 minutes only, right? So this beautiful step strand experiment teaches us that the waiting time is your network's lifetime. So what's plotted in red was the step strand of different levels. You find if you stretch more, you wait less time, see? What's plotted is how much you stretched and waited. That's the red. And it turns out you can do the continuous. You find the breaking in continuous stretching matches in the sense the slower you stretch, because you're given enough time, the lifetime, and you only need a small amount of stretching. So basically, this confirms my theory that the reason you break is you reach the lifetime of this. So one of the last one was this very intriguing. We all grew up with this TTS or TTE, time-temperature superposition, except we have time-temperature superposition that has nothing to do with polymer relaxation times, but having to do with a newly identified internal timescale or clock called polymer network lifetime. And you can do this cute thing to match. When you go to high temperature, because the lifetime is shorter now because of the activate process, you just use higher rate. At the lower temperature, you just lower rate. I can predict that you will break at the same strand. That's TTX. And that's this plot. I confirm it with a step strand and so on. Okay, I run out of time. And in fact, there's one more topic very interesting I'm going to skip. So that's the conclusion. That's it. I'm on time.